before we talk about the learnings from the field, I will provide a quick recap for the asynchronous event-driven programming model that Node.js presents, so that anybody who is interested or who wants to go back to the basics can essentially get a grip on that. So the learnings can become pretty handy. To understand what is the pioneering technique of Node.js, what is all about the event-driven programming, let's look at this specific chart. So this table has two columns. One is the device or the endpoint in a computing area, and then second column shows the latency. So as you can see, some of the items like the CPU registers, the cache, the main memory, etc. are provided, and the latency is the amount of time that's required for transporting a piece of memory from one location to another. So for example, the first row shows what is the time required for a byte of memory to be transported between two registers, and the last one shows what is the time required for a byte of same data to be transported between two network endpoints. So as you can see, the latency increases as we go downwards, and I put a red marker in between, not exactly in the middle, but there is a clear demarcation that you can see. Can somebody point out what the classification is? It's basically anything that is above the red line, the data can be transported with very little amount of time, sub-zero nanosecond. The CPU registers which are inbuilt into the chip, you can transport in the range of like gigahertz frequency machine, meaning you can transport in 1 by 10 to the power 12 seconds. So that's almost like 0. Whereas when it comes to the network endpoint transportation, it takes 150 million nanosecond, which is almost like 150 milliseconds. So clearly we see the latency between different endpoints. But what does this mean to the programs? Essentially, a program is a mixture of accessing CPU registers, doing some computation, reading from the network, writing into the network, accessing disk, so on and so forth, in seemingly arbitrary manner. So it's a mix of all these operations, any program you take about. But is there any insight that we can glean from this? That's exactly the Node.js architects thought about. We classify anything above the red line as CPU bound operation, because all those things are executed pretty much as fast as between two CPU registers, whereas anything that is using the last three rows is classified as IO bound operations, because they involve IO, they involve accessing some peripheral devices which require some device drivers to come in and do some additional tasks for you to transport between your system and another system, with a kernel coming in between and interpreting things like that. So if you take a typical program, a notepad application, desktop application, or a web application, you will see any tiny program will involve both CPU bound operation and an IO bound operation. So for example, you're doing a computation, you need to feed in the input, which is an IO. You need to do the actual computation, which is a CPU bound. If you take a web application, for example, it requires an input to be provided by the client, and the server does some computation or processing on the request, and then finally comes back with a response. So the request and the response are IO bound. The intermediary computation that happens in the backend is CPU bound. So what is so big deal about web application compared with any desktop application? Seemingly no difference. But if you look little deeper, you see that a notepad or a calculator application has a one-to-one correspondence between CPU and IO bound operation. Because it's a single user system, single user is interacting with the program. So one computation meaning one IO. Whereas when it comes to web application, one web app interacting with millions of users or thousands of users, that means it is dense with IO operations. So that means if you have a typical microservice or a web application, it will really slow down, or the performance will be a function of how many IO bound operations are there in the system. Now, architecturally, if you look at a way for separating the IO bound operation from the CPU bound operation, you can say that all the CPU bound operation can run pretty fast while pushing the IO bound operation for being executed in another channel, and let them execute at its own pace. And once those operations are complete, we will post process that and fuse it with the CPU bound logic and make the original logic come back to the presentation. So that's the whole idea of the event driven architecture. That's a lot of theory. Now coming to the practice. Here is a pictorial representation of the same thing. You have three columns. First one is a set of code. Second one is some abstractions belonging to the Node.js runtime. Third one is the output. So if you look at the first call, which is a DNS lookup, and that's an IO bound operation, you need to connect with the server, get the IP address or get the well-known name and get back. So that involves a network operation. Because it's an IO operation, it's going to take 150 million times more than the CPU bound operation. You push it to an abstraction called DNS, which in turn makes a request to the dark purple circle in the middle, and it immediately returns a control back to the next code as if the code is executed, right? Actually, the code is not executed. It's going to take a lot of time, but I'm not going to wait as a blocking thread. I just come back, execute the next piece of code, which is a file access. Now, file access is again an IO operation. It does the same thing, but it requests with another abstraction called file, which in turn invokes the dark purple circle, which is the dark purple abstraction is called event loop or libuv. Returns a control flow immediately, execute the next one, which is a network page access. Exactly IO bound, and the next one you execute a timer loop, a delayed execution for a second. It follows the same suit, it goes to the abstraction and comes back, and finally you execute a console log and print something. Now that doesn't undergo any abstraction because you can directly print to the console, it executes immediately. Now if you look at the right hand side, you see the last line that is requested by the program is returned or is executed first, because it doesn't need an IO, it doesn't need a blocking call, it can execute immediately. Then the FSCB, which is the callback of the second operation, gets executed. Then the DNS CB, which is the first call, and then the network CB, because it takes more time than anything else, and finally the timer CB gets executed. So the learning from this is things get executed in the order of completion from the IO channel, not necessarily in the order in which you wrote the program. Second learning, the callbacks or the completion handlers are executed exactly at the time when those are executed in the backend. So there is no dependency between calls and operations. Now that piece of proof or that piece of finding, that piece of insight is the core of asynchronous programming. And for that, Node.js need to be written in JavaScript, because JavaScript provides the way of writing callbacks, which will remember the context in which your original code was called. Say for example, I need to do something with the DNS CB which was requested earlier, and I need to be in the same context when the completion happens. So there is something called closure, and JavaScript is a first class language which implements closure. And then you also need to change the way the code is compiled and executed. For that we have the libuv, also called event loop, and with the whole mechanism in place, what you get at the end of the day is 30 times faster code, or code which is performing 30 times than the traditional sequential program. It's not 30% improvement, it is 30 times, right? when you think about a typical web application, because no blocking call is there. Everything is executed in sequence as fast as you can. Anything that is blocking is pushed to the backend, and as and when the backend is completing it, you are able to provide the callback or the completion handler for that. There is only one thread. So, yeah, because of this disparity, like 0 or 7 or 25 versus 10 million, 150 million latency disparity, we are able to execute everything that is in the left hand side, everything that can be possible in a jiffy. Then we are waiting. The single thread in the system is actually waiting because all the IO are happening in the backend. Yes. Yes. In Java, what happens is you make a read request and you block the thread, right? So you can utilize the cores only if required. What if a single thread is able to handle all these things, as the inefficiency will come only when FSCB return, but the single thread in the system is busy at that point in time and is not able to execute the callback, right? So that scenario will happen if your program is heavily loaded with millions of concurrent connections happening at that point in time, and your system having multi-core. So only one CPU is engaged, the other CPUs are not engaged. That's the problem you are talking about. So in that case, there is a utility called cluster, which is an API, Node.js API, which will help you parallelize the request response cycles, by which another process will be spawned to leverage the additional cores. Sure. So if you transform this pieces of code with a real request response cycle, real web request, first a web request comes, you are able to parse it because it's all CPU bound. Somewhere down the line, you encounter a database call. So you push it to the abstraction, one of these abstraction, network abstraction, because database is across the network, and then database is taking milliseconds, which is quite huge compared to the CPU bound operations. So nothing to do for this request, right? So you switch to the next request. Yes, client has been waiting. Otherwise, also if you take a Java call, there also it's blocking, right? So in Java, how this scalability is implemented is using thread pool. So one thread got blocked, and that shouldn't make the whole process blocking. So you implement a thread pool, you keep number of threads keep alive, and as soon as threads get blocked, you engage in Java or no, in Node there is only one thread, and the proof of performance, proof is the performance itself, right? It's able to come back. Say for example, in this case database, it's able to do everything with the concurrent request as much as possible, and then it is idle for most of the time, waiting for one of the database of one of the user to come back. Now at that instance of time, it's only the database return that is in the context, and it's able to complete that, push back the response to the client, and still the thread is free. So I mean, if you see this disparity, correct? If you see this disparity, I am able to execute millions of instructions in the CPU before I could actually wait for or complete one IO bound operation. Am I clear on that? Or yes. So that is the mechanism by this and this sort of callbacks. So the callbacks are passed to this blue abstraction. Blue abstraction passes it to the purple abstraction. So purple abstraction is the guy who actually intercepts the database return. Okay. So that time it has both the database return data, whether the query result or error, whatever, and it also has the function that needs to be called back in that context. Even thread, actually kernel, that interacts with the kernel, and kernel has many threads to execute things parallelly. If this guy, that guy doesn't have threads. It's the kernel who has the threads. Yeah. So we are leveraging the kernel to the best possible extent. Yeah. Good. Are we good? Okay. So this is a recap of Node.js. My actual talk today was 5 learnings from the field. Let's get into that. So the first one, as I said, I will talk about the problem as reported by the customer. How did we diagnose it and what are the learnings? So the first one, for everything I actually quoted the real issue from the GitHub. Here the customer is reporting a high RSS. So RSS stands for resident set size, which is basically a measure of memory in your program. So we know about virtual memory. Virtual memory is the amount of memory your program has allocated. But at any instance of time, not all the allocated memory will be active in your process. So the memory allocated by you is subjected for paging. For example, if you have a lot of concurrent process running, at some point in time, the operating system will purge or take away some part of the memory which you are not actively using and lend it to the other process. Of course, it will write down whatever the content of the page so that it's not cluttered. And when you request for the page, it will be given back to you. So that's called the general paging swapping concept. So that essentially means RSS will be much lesser than the actual virtual memory which is requested by your process using malloc or new or whatever the object creation routine. In this case, customer is saying that I know I've been requesting huge memory. I exactly know the place, but I also know that all those memory has been deallocated, right? I've been creating a lot of arrays and objects and I was putting in the cache, but I cleared the cache. So I exactly know where these are collected. I can also see the garbage collection log, which says that these are all purged from my process. So I shouldn't be accounted for these memory. So the reported problem is exactly the reverse of virtual memory RSS logic. You have a tiny amount of virtual memory, but the RSS measured is very, very huge. That's the problem. So this is absolutely surprising. We cannot what you say relate to that any real world scenario. So low heap usage but very high RSS, and once the RSS goes up, we have seen that it's never coming down. That's a symptom as reported by the user. So how did we diagnose it? We looked at the JavaScript heap or Java heap based on which language you are talking about. We faced with problem of how to measure the memory. This is not visible, right? You need to have some tools to figure out what is the actual memory. We use tools, and tool says this is 2 gigabytes is your memory. How do you trust it? Because somebody says no, this cannot be. One tool says this is. So then you need to have a mechanism outside of both the tools and the runtime to validate both the parties to figure out who is right and who is wrong. So that needed a lot of exercise. And plus, it's not easy to diagnose where the memory is allocated and deallocated in the Node.js runtime. Node.js runtime, Java runtime, these are quite huge and complex. You can't put some printf and things like that in one part. It's a combination of a lot of modules, C++, JavaScript and C, lot of languages fused together. That's what is Node.js runtime. And same is JVM. So the way we worked out is simulate the pattern of memory allocation, deallocation through small C, C++ sample programs. We followed the way Node.js runtime and the customer's application program were allocating memory exactly almost in the same manner in our dummy application. So it involves allocating in chunks, deallocating in chunks, allocating in huge volume, allocating in small volume, allocating in small numbers, huge numbers, and deallocating in different patterns, so on and so forth. There can be, yeah. I mean, these are programs written by developers, so there also can be bugs. So, okay, I am a Node.js developer, so I am talking from the perspective of the reported problem against the Node.js runtime, not against the application. So application developers debug the problem. They understood that it's not their problem. No leak in the customer's application. Then it has to be Node.js runtime. That's how it was reported against us. So now we need to look from the runtime itself. Runtime is also a piece of code which also has garbage collection at different levels. So we are debugging at that level. So we did basically simulation testing to mimic and reproduce the same problem in different platforms. We could change platforms. We saw that RSS once, and we could recreate the problem. RSS once increase reduce only in response to memory demand from the system. If the system is loaded, sorry. So this was a big learning. What we have learned is, as I said, RSS is the amount of active memory in the system, and RSS reduces when another process is requesting memory which is held by your process, and there is no other memory left in the system. So that's where the paging happens. But what if your system is relatively free in terms of memory? Say, for example, you have 32 GB memory, and your process is once it used say 30 GB at some point in time, huge cache and all those things, but then you deallocated everything. So ideally your RSS should come down, but because nobody else is requesting memory, this 30 GB which was once allocated was actually retained as is. That was the problem, and it's so funny. We were surprised to see that maybe this is a bug in one variant of Linux or specific operating. This cannot be Node.js problem. This cannot be application problem. This has to be some logic in the operating system. Then we tested in various versions of Linux. We tested in other platforms like Windows and AIX and things like that. Then the realization came that this is a design across the board. Everybody does that. You know, it's a non-fixed bug in the OS. I don't know it's a bug. Some OS folks say that it is by design, because there is no need to bring down the RSS. If you want to bring down the RSS in response to nothing, you will need to keep querying the process. Hey, which process is not using memory? Let me purge it. It's not required, is what the operating system vendors say. But then the problem is, if you are measuring the efficiency of your process by RSS, then your numbers are going not to tally, right? There is no harm to your process. It's just that this number is tallied against you. But then there is a visible problem if you are using cloud, and most of the cloud vendors charge you by memory, and they will look at RSS. They won't look at the virtual memory, right? So your process will be accounted more than what actually it deserves, or more than what it's actually used. So it's a big learning. I just wanted to share this experience because you should be aware of this. That's the first story. Second story is more Node.js specific, because this is something called as exit race. So Node.js, I said Node.js is single threaded, which is true and false. From the application's point of view, it's a single thread. That means the JavaScript is always executed by single thread. But for improving the performance behind the scene, there are some pool threads running to say run concurrent garbage collections, or to do some disk reading, which is asynchronous, or to talk to some operating system in an asynchronous manner. These are helper threads to do specific tasks. So we have seen random crashes in the Node.js application, and reported by many customers, not just one. So the symptoms vary from scenario to scenario. We get SIG-ILL, which means illegal instruction. We get SIG-ABRT, which means SIG-abort, which essentially means the process tries to execute some instructions in a bad way, right? And zigzag V is a very popular signal, which essentially means a process try to access memory which doesn't belong to it. So problem determination was pretty tricky because it was not consistent. If you run it 100 times, you fail twice or thrice. And when you do, usually when you see a problem, what you do is you do bisect, git bisect. Anybody knows git bisect? It's basically go back to a state in the code base where you know it is stable. Come back to the place where you know it is definitely a problem. Then you do the binary division. Come to the middle, see what happens. If it happens, come to the right hand side. If it doesn't happen, go to the left hand side and repeat the same thing in a loop. That is called git bisect. So git bisect can be really hectic based on how many comments you got. So we did that, and finally the culprit commit that we got had nothing to do with this sort of a problem. So that was another roadblock. The change had nothing to do with the thread or concurrency or race condition, nothing. So that could essentially mean that it's a timing issue. The culprit commit is not really causing the problem, but it is altering the timing in such a manner that original problem exited somewhere else due to some other bug is actually manifested because of this bug, manifested because of this commit, because it increased a timing window or decreased the timing window. So then we dug deeper, and some of the findings, some of the clues that we got is the crash was always happening when the Node.js was exiting. As long as it's running, everything was fine. But when you shut it down or when the event loop is exiting, that's the time the crash is happening. So then with that hint, when we debug, we figured out that the order in which the Node.js is initialized, like creating, there are a lot of data structures and entities and components that you need to initialize when the Node.js runtime comes into life. These are called array buffer, isolates and platforms and event loops and threads and garbage collector, virtual machine interpreter, JIT compiler. So many components are there. You initialize in a specific order, and in that order you also create some threads and data structures and put it in some place and make an association. Now when you exit the runtime, you need to do it exactly in the reverse order. If you change the order, things can go really bad, and that was the actual cause. And in some commit, they were changing the order as a side effect of some other bug fixing. So the the tools that we use is GDB, LLDB. LLDB stands for low level debugger belonging to LLVM project. LLNode is a customization of LLDB for the Node.js project, and tracing is a typical method tracing. And we did instrumentation, and to make the problem much more pronounced and visible, we could inject timing delays in the application. So that's a known problem determination technique. If the recreation frequency is rare, we could add or remove some timing, and keep doing that and see if the frequency changes. And if you found that, then you can do that much more, then bring the frequency much more increased, and that can actually save a lot of time in your problem determination. So the fix was to basically understand the creation order and follow the same order in the time of destruction. Pretty simple fix, but the debugging was really hard. The third one, which is data bifurcation when pipes are repiped. So pipe is a low level concept. Pipe belongs to something called IPC, inter-process communication. The traditional Unix programs used to be very much focused on isolation between processes with roles and security and so many other things, visibility, things like that. So there are few mechanisms if you want to talk between two processes. Socket is one thing, pipe is one thing, file is another thing, and I think a couple of other things are there. So pipes are basically to connect between processes. If you say cat foo.txt, pipe, grep, do something. So the cat process uh, output is connected with the input of the grep. So the, 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 every process comes with three streams: std in, std out, and std error. So when you do the piping, the output of the parent process or the first process is duplicated, and similarly the input of the child process is also duplicated, and they close one end of the pipe from both the sides, and then they close the input stream of the child and output stream of the child. So the duplicated output of the parent now becomes the input stream of the child when the forking happens. Because when the forking happens, this duplicated file descriptor gets copied to the child process. The fork is a system called which copies everything from one process to another, and then you delete or you remove unwanted things and start continuing from where you want to. The only thing that gets transplanted from the parent is this duplicated file descriptor, and that's the way the IPC piping mechanism works. Now, in this specific case, customer reported arbitrary data truncation when a process with a pipe is spawned. So that means a process has been running, it has a pipe, it is communicating with another process. Now suddenly you create a child process out of it. You see the data that was supposed to go to the first child or other process is now getting truncated or bifurcated. Some data is going to the second child, some data is going to the first child, which is completely undesired. So again, this was not consistent. A lot of times we see problem is not happening, problem is happening, and things like that. It's really difficult to trace because the data coming through the pipe you can only read and you can only trust what has come. There is no way peeping into the pipe. So the actual problem was when you are repiping, you duplicate the existing pipe, which is already duplicate of the parent pipe or parent file descriptor. And when you do forking or the child process, this duplicated file descriptor again gets duplicated. So basically you get 4 instances of the same original file descriptor, and you are supposed to close 3 out of it rather than 2 in the actual code base. We were actually forgetting to close one part of the descriptor, which was basically resulting in data getting confused. When somebody is writing into a file descriptor, it has 2 ends to write into. So it was writing into the 2. One was getting into the legitimate child and one was going to the other one. So once we actually started tracing, we understood that no data is lost. Part of data is going to one child and another one. The rest is going to the other child, which is obviously undesirable. But once we understood that part of the data is going to the other child, we know the problem and we fixed it. Basically, the fix is to close every file descriptors other than the one which is intended for. The tools we used is tracing. S-tracing is low-level tracing at the system call level. Basically, Linux tracing. GDB is for debugging, and methodology is again we were able to locally recreate the problem. The fourth one is shutting down Node.js in flight. So this is a feature request requested by one of the enterprise product. What they were doing is they were embedding Node.js in their C++ application. So think about a message queue or a large message bus, and they want to communicate between different components, different programs. Now the way they implemented is having a single program which embeds Java, Node.js, and Python and Ruby and all sort of things in a native way, and they intercept the message and they pass it on to these embedded programs without really making use of any message queue or any IPC. Because these are in-process programs, they it was very easy to transport the data in process. But the RFE or the feature they requested is when Node.js is exiting, sorry, they wanted to exit the Node.js, but Node.js doesn't exit at will. The only way it exits is when there is no events in the event loop, right? All the events are drained in the loop. That's the time it exit the loop, exit the process. But what happens when you, as part of the transaction, you want to shut down Node and bring up Python or something else? How do you kill the Node.js? If you send a signal, you are actually sending the signal to the whole process, and everything comes down. So that is not desirable. You need to have a mechanism to drain the event loop and then hold down the Node.js part alone and continue with the rest of the process. So that was an RFE. It was not a problem. I mentioned it here because it's an interesting architectural scenario. The original design of Node.js never wanted to shut it down on user request, but it shuts down naturally in response to having no events in the system. So we fixed it by introducing an API which can be called from another thread than the Node.js main thread, which can invoke the API to shut down the node, and it will go into the event loop and look at which are the events present over there and inject an event or a request to each of the event to Quest, and then it will return. Eventually the event loop will become empty, and that will initiate the Node.js shutdown process. So we get a clean exit. Everything else will be in place. Here is the last one. This is flexible STD IOs for IPC. This is very interesting. If you have a child process which is writing some huge text or huge output and then exiting immediately, customers have seen that the text is not written completely. So the problem is by design. What happens is the console.log is asynchronous in nature. Everything in Node.js is asynchronous in nature. So when you say huge buffer, 1 MB buffer is returned to the console, before it could write completely into the console, you are exiting. So the exit takes precedence. Exit means exit. If you call the C the low level exit, nothing is continued further. It's like an emergency exit. Everything is cleaned up immediately. Ideally, if a console.log is being processed, you shouldn't be exiting, or at least you should wait until that printf is completed and then exit. So this is a huge design flow in Node.js. If you want to make it work properly, you need to make console.log synchronous, blocking call. The moment you introduce a blocking call, everything else, anybody writing a console.log in any of the part of the application, including an NPM module, everything gets stuck over there. Yeah, never block the event loop. Yeah, if you follow that principle, this problem exists. So it is still an open bug. It's a design limitation, but many people in the community try to implement or address this problem in their own way, but it's still not resolved, and there are several debates on that. We have so many open issues in the backlog, but even before that, I mean, a lot of interesting stories. These are some 5 samples which I collected from my experience and thought could be useful for people, and this also is a foolproof manifestation that there is a large scale adoption, because complex problems only come from large scale usage and adoption, right? And definitely the number of days or number of hours we spend on diagnosing and debugging these problems indicate that there is a definite space for improvement in terms of the tooling and other methodologies and best practices. So the one I want to focus here is a lot of open issues in the backlog. I think 1,000 plus last time I checked. A lot of PRs. and our community is not quite huge. People definitely in the open source, everybody knows people work on a voluntary basis. Some companies pay for working in the open, but not everybody. IBM pays for working in Node.js because it's a strategic platform for IBM. There are a lot of products based on that, but that is not sufficient. Still, there are, there are many companies like Google and Oracle and Microsoft paying and spending a lot of time, but it's not sufficient. Still, there are a lot of issues and a lot of opportunities. So, the call for action or the messaging from my point of view is Node.js is a cool platform. It's a good community, very inclusive, very open, very transparent, and very helpful. So, there are special programs for newcomers. Like if you don't have any idea about Node.js, but you have little amount of understanding about JavaScript and programming, there are plans and there are contributions which we kept for newcomers. The whole idea is to make the onboarding very easy and then help with the handhold newcomers so that they get a good experience and then eventually become a contributor, eventually become a committer, and then a leader. So I would entreat and request you to have a look at the Node.js repo, which is github.com/nodejs/node, and go through the issues or the opportunities out there, whichever is suiting your skills and interests. Like there are C++ in which the core platform is written. Then there is a JavaScript module which implements the APIs, the console.log and all sort of things which are pure JavaScript. Then there are markup languages in which documentation is written. Then Python, which implements the tooling. So we have a whole lot of spectrum of languages. Based on your taste, you can pick up any and start by improving the testing, documentation, triaging issues, and pick choose some item and implement of your own. So all combinations are available. Just try it out, and as we know, open source is a good it adds good contribution to your resume. So having some strategically important project in your portfolio will be really good. If you look at in terms of adoption, user downloads and number of stars, that's how we rate the GitHub projects. So Node.js originally was number 3 after Bootstrap and some other project, but it keeps varying from year to year. So it's anyway in the top 10 or 20. So that much I can guarantee. So having that in your resume is really going to be good. So just wanted to state that as a corollary or as a summary. That's pretty much I had. Thank you very much.